Alright, let's continue this Atwood machine problem. So the next part here asks, or says, assume the abbot weighed 200 pounds and the novice weighed 100 pounds. This event occurred before the British adopted the metric system. Calculate the acceleration of the novice and the abbot's descendant. Alright, so this is easy because all this part here is having us basically plug in chug. Let's see, so I'm going to do a little bit more math fun tricks here. Let's see, so let's just note that when we're talking about the force of gravity on the abbot, we can express that mathematically as twice the force of gravity on the novice, since the abbot's 200 pounds and the novice is 100 pounds. Right? Or, we could write this a little bit more conveniently for this problem as 1/2 the weight of the abbot is equal to the weight of the novice. Alright? So that's going to be useful because now, for expression for acceleration, we can plug in for the weight of the novice 1/2 weight of the abbot, and that'll help simplify our formula a bit. So I'll have my acceleration equal to, in our numerator, we have the weight of the abbot minus the weight of the novice. So minus 1/2 weight of the abbot divided by the weight of the abbot plus 1/2 weight of the abbot. All that times the acceleration due to gravity. All right, so kind of looking at this in my numerator, that leaves us with just 1/2 weight of the abbot divided by my denominator, which is 3/2 weight of the abbot, all times acceleration due to gravity. 1/2 divided by 3/2, force of gravity here cancels out, so we're left with, let's see, the twos cancel, and then we have acceleration due to gravity divided by 3. And then I guess we'll round this to numbers, right? Because right now my answer has an infinite number of significant figures, because G is precisely, it's infinitely precise, I should really say. It's like writing the letter pi, or I should say writing the number pi. So let's see, looks like we've got 3 significant figures in this problem, so this gives us 3.33 for using 10 meters per second squared for G. Meters per second squared. Alright, so there is our acceleration value. And we should really be a little bit more precise here. It does not say compute the magnitude acceleration, it just says acceleration. So we should be careful and include direction, and we're not going to get points off for that. And the novice is accelerated upward. Alright, this number seems reasonable, right? Because we know that our number should be smaller than the acceleration due to gravity, because that would mean that our novice is in free fall, which they're not, right? They're going to be slowed down a bit because of this tension of the rope. So having it be smaller than the acceleration due to gravity makes sense. Alright, so one last part for this problem. Let's calculate the time interval for the descent of the abbot. When the abbot reached the floor, he released his end of the rope. Calculate the time interval for the descent of the novice. Alright. So if you look back at the prompt, so again, I'm going to scroll here. The prompt had this information that when the abbot stepped off the platform, grabbing his end of the rope, it was 2.5 meters from the floor. Right? So they provided us basically some kinematic information. So kind of sketching that here, and since we're calling for the abbot downward being positive, right, we're calling downward positive y, it's going to be convenient to say, well, let's say the abbot started at some height here of 0, and then traveled a positive distance of 2.5 meters. Right, that's going to be a convenient coordinate system based on our situation. So computing the time it takes to fall, we know values here going on for distance. We're trying to solve for time, so let's use the position equation. So we have final position is initial position plus, well, here I'm using x's and I said in my y direction, so maybe I'll write this in terms of y. Final height is initial height plus my initial y component of the vertical velocity times time plus 1/2 my acceleration times time squared, and technically this is the y acceleration. Alright, so plugging in these zeros, I'm saying that we start from a 0 height. The abbot also starts from rest, so that whole term is 0, which is very convenient, and nothing else here is 0. So we have that y is equal to 1/2 acceleration times time squared. So rearranging here, solving for time, we end up with the expression that time is the square root of 2 times y divided by the acceleration. So that's going to be square root of 2, and sorry that y looks a lot like a g, that's a y. So 2 times our 2.5 meters divided by the acceleration we just found, 3.33. I'll use another 3 here for significant figures so I don't have rounding error. I say that and yet I use 10 meters per second squared instead of 9.8, but I digress. After doing the math here, we end up with 1.2 seconds. So it takes 1.2 seconds for the abbot to fall. Now, calculate the time interval for the descent of the novice. So let's see here. The prompt here says that when the abbot reached the floor, he releases his end of the rope. Right? So the rope is now slack. It's not taut. So this means that tension is now 0. There's no tension in the rope. So therefore, our novice is now going to be in free fall, since the only force acting on it is gravity, since the rope is slack. So for our novice in free fall, again, we have this same descent being the same height, because he's going to, if the abbot lowers 2.5 meters, when the rope is attached, the novice will raise 2.5 meters, and that's when the rope becomes slack, and now he's in free fall. So we end up with the expression, so using, again, the position equation, we have y is equal to 1/2 gt squared, since my acceleration is now the acceleration due to gravity. So then time was simply 2 times y divided by the acceleration due to gravity. So same expression, but now my acceleration is precisely that instead of the number computed. And that gives us 0.71. I'm being, I think, inappropriate here with sig figs. I should have one more sig fig, but I didn't compute it when I wrote it down, so sorry about that. And same thing for the previous answer, but we've got 0.71 seconds. So it takes less time for the novice to fall, but again, that makes sense because it's in free fall, so it has a faster acceleration, or I should say a larger acceleration.